So yeah, I'm Sebastian B.Holgersson. I've worked with software for about a dozen years, something like that. I've worked in a bunch of different domains. I've worked at Sony a long time ago, working on the Android project there. I've been a consultant, doing a lot of web, doing a lot of cloud, doing a lot of CI/CD, DevOps, type of thing. And yeah, my presentation is going to be kind of a generic introduction to CI, CD, and CD, the two different CDs. There's going to be some talk about how to build your own pipeline. It's going to be talk about how we've built our pipeline that integrates both Cantata, integrates the Codesonar, and how you can kind of integrate any tool to a pipeline. And I thought I'd start with this phrase from the Agile Manifesto. The Agile Manifesto is kind of where continuous delivery and to some extent continuous integration kind of starts out. Is where you see continuous delivery for the first time, like this. And the quote is, "Our highest priority is to satisfy the customer through early and continuous delivery of valuable software." And this is kind of like the definition of continuous delivery. So Agile, continuous integration, continuous delivery, and all these, they kind of started existing during the IT, not to call it the IT bubble of the 90s and early 2000s. Basically, where people wanted to deliver software at a more rapid pace and have more, instead of having these like long delivery cycles where something might take years or months, years, whatever, to get software out to your customer. You wanted to do it in a quick way and get it out basically as soon as it's ready to be released. So Agile methodology can be seen as kind of like a reaction to waterfall, where with waterfall you have like this setup where you do like a big planning design phase, you have a development phase, then you have a like a testing phase, and then like a maintenance phase, and all these phases. With Agile, you kind of, instead of having these phases where you go through them once, you iterate and do it often, basically. This means that if you make a mistake in your planning or design phase, you can make up for it in the next iteration of your work. Right, so there's two different CDs and one CI, and my hope now is to kind of define them as I see it. These are like, there's no like group that says this is CI, this is CD, and it's like the authority on the matter. But this is kind of like how I see them and how I work with them in my years as a developer. So I'm starting out with continuous integration. Continuous integration is kind of the thing that I've never seen anyone actually do properly, because it's also a problem that I kind of don't see very often these days, but it's one that can exist. And certainly like a decade ago, I saw it quite often. These days, people kind of have this worked out, I think, to some degree. But the reason people want a continuous integration is something like this. So you have a delivery phase here, where on January 1st, you decided you want to add all these features to the next version of the software, which is going to be released at the end of the year. These are just kind of like some random made up features. So you might want to add improve database performance, add the dashboard, migrate environments, all this stuff. And you want to do that by December 31st, and that's going to be your version 2.0. Between here and there, you're not going to be releasing anything, or we might do like maintenance releases. So in a non-functional, in a project where you're not using continuous integration, it might look something like this. So you have 4 different teams. Maybe you have the user interface team. They're working on adding the dashboard. You have the database team. They're normalizing the payments table. You have the operations team, they're migrating to Java 17, and you have the payments team, which is adding support for Dogecoin, apparently. And they all work separately. They don't interact with each other. They're all siloed off. So December 15th, they all merge their work. You have basically one big integration day, and things are not going to turn out well for them, because so these people here work with the assumption that they're running Java, I don't know, 11, let's say that. And then they migrate to Java 17, and suddenly their setup here is not going to be working anymore. Normalizing the payments table might not work with this. They're adding a completely new feature, which might not be congruent with the user interface changes that have been made up here. And basically, from December 15th until December 31st, you're in what's called integration hell, where all these different teams are now going to have to basically be scrambling to fix all these bugs and issues that have been added towards the end of basically the iteration, which is the whole year. And this is going to be a problem. Most likely, they're not going to be releasing on December 31st, especially if they're planning any kind of Christmas vacation. Yeah, so this is kind of like the problem that continuous integration wants to solve. And the way it does so is by basically finding these pain points. Like here, the pain point is integrating all these different features and having a product that works by the end of it. And the solution is to do things more often that are painful, but if it hurts, do it more often, which is kind of like a mantra in Agile and CI circles. Basically, you want to find your pain points, which in this process here is integration, and basically do it more often and do it in smaller bursts. So instead of integrating all these features on December 15th, it might look something more like this. Maybe the user interface people, they refactor the dashboard library, and they do that early in the year. The database people might normalize the payments table. They do that very early in the year. And these people all work towards a single main branch where they push their changes so that when the operations team is migrating to Java 17, they're going to be doing that on the same branch of code that the database and the user interface people are working on. This means that you're going to have loads of small integration pains, like maybe this dashboard refactor that's made up here doesn't work with Java 17. You're going to find out early, and you're going to fix these issues somewhere around here, like in January maybe, rather than doing it towards the end of your delivery cycle. And this is basically continuous integration. One problem that comes with this is if someone breaks this build here somewhere, like maybe this migration to Java 17 just breaks everything, nothing works anymore. It's going to stop all this development from the other teams. The solution to this is to basically ensure that this main branch of code that everyone is working off is working at all times. Basically, you want to create test cases, you want to have static code analysis, you want to basically ensuring that at any point when a change is made, you have not regressed, you've not made the state of the application worse. And this is basically what continuous integration is wanting to ensure, that the main branch is at all times clean and functional, or there are tests that cover all the functionality, the static code analysis that ensures that the code looks the way you want it to and doesn't have like obvious issues like memory issues and so on. Yeah. There we go. Yeah, and so the solution to this is then integrate often, add automation basically to ensure that the main branch of code is working the way it's intended to work. Because if you're going to have like manual testers validating the entire state of the software every time someone in any team makes a change, you're going to have a problem. They're basically going to be the bottleneck that's going to delay your entire process. You can use feature flags. Basically, if you have a feature that's not fully done yet, you can use a feature flag to say this needs to be enabled before it goes out into production. And yeah, if you break the main branch, you want to be fixing it immediately. Basically, that's all hands on deck. Make sure that stuff works. And you have short iterations. So instead of having an iteration like we saw here, where they go a whole year before they go back and like reassess and test, you want to be kind of doing that often. If you're talking like Scrum, it might be like every 2-3 weeks, something like that. Another thing that's funny with the continuous integration that kind of isn't practiced from what I've seen is when people say integrate often, it means like very often. It means usually you want to be pushing your code on a daily basis into the main branch. Basically, this is so that you don't kind of diverge and have like a bunch of feature branches that live for weeks. And then when you integrate them, you're going to have a smaller version of integration health. Basically, if you integrate often, you're going to have smaller integration health. I don't see that done very often, but like if you want to go by the book, that's how you're meant to do it. Like integrate to the main line on a daily basis. That can be difficult to do. Continuous delivery is kind of the next stage of this. So with continuous integration, we've made sure that we can basically push our code to a main branch continuously, and that the build as it isn't broken, all the tests pass, static code analysis is happy, and so on. Continuous delivery adds basically a packaging step to this, where in continuous delivery, what we have here is continuous integration, the same diagram we saw before. With continuous delivery, you add basically a packaging step where you want to be sure that you can release at any point. So you would be continuously creating these deliveries, like say here 2.0 release candidate 7, and you should basically be able to, at the click of a button, deploy this into production and make sure that you won't break things. From a functional safety perspective, I would say continuous delivery is probably quite difficult because you have a lot of other considerations, and then we'll talk about that later. The reason you want to be doing this is that this packaging phase and the delivery, the testing, possibly certifications and so on, they should be a routine process. It should not be something that you do once a year or something. You should be very comfortable packaging, testing, and doing all these things that need to be done for a release. And this kind of forces you to automate these steps as well. This could be stuff like maybe like more thorough integration testing, maybe end-to-end testing that would not fit inside a normal continuous integration pipeline. So continuous delivery might be done where continuous integration is done on a daily basis, ideally. Continuous delivery might not be a daily thing. It might be something you do like maybe every sprint. But you should be able to like deliver whatever you create here to a customer, and it should work. It should not have regressions. Doesn't mean you actually do it, but you should have that process of being able to at any point just kind of like release, and everything should be fine. And then continuous deployment is the step after continuous delivery, where you not only create these release candidates, you actually push them into production on a daily basis. And so this is probably very web friendly. Like if you're talking like Facebook, they probably update their application, I don't know, 20, 30 times a day easily. But it's kind of an unlikely thing to do in a lot of other domains. Like, I wouldn't want my car to update every day, especially if it changes like the driving characteristics or something. Like, this is something that works in certain domains, but I would not recommend it in every domain. The advantage of this is that you also have to automate a lot of stuff, and that automation is going to let you work a lot faster, let you release a lot faster. It'll remove all the drama of a release. So, for instance, if you're deploying constantly, you will need to have stuff like a blue-green deployment, for instance, where you can basically quickly roll back to the previous version, even in production. And this type of thing basically requires that you work according to continuous deployment, where you will be deploying constantly, and you will be basically automating the entire flow from code coming in to code being in production, being served to the customer. So then we come to functional safety, where we kind of have to ask if any of this is applicable. Because, I mean, continuous integration is something that it really helps if you have a large team that works on the same branch of code or the same code unit, basically. Continuous delivery. Well, so if you're going to be packaging something that is ready to be deployed to a customer continuously, that means you need to be, like, for instance, certifying constantly, like every couple of weeks. You need to make sure that you have like all your certification documentation, you have all the tests have been executed. You might need stuff like what's it called? Actual working tests on hardware. Basically, you have a lot of difficulties with functional safety that don't exist in other domains. So, for instance, you have like strict documentation requirements. And this can be difficult to do. If you're going to be pushing every single day, you also need to update all this documentation every single day, because you want this kind of like, you want a congruent system and documentation. They should not be like deviating. You have third-party certification bodies. Maybe a third party has to certify your software. That can be difficult to do on a daily basis. Deployments can last for decades. I mean, it's entirely possible that you deploy a functional safety application to something that might not have internet connectivity or might not want to update on a daily basis. You have stuff like manual review, where, I mean, often you have manual review in other cases as well, but you usually have a lot more manual review in functional safety cases. You might need to train the people who will be using the application. You can't just throw out a new, I don't know, medical device application thing without training the people who will be using it, because that can have a lot of consequences on the safety of the people who are using it. Testing might need to be done on actual hardware, and you might not have like, if you work in the automotive industry, you might not have a whole car that's hooked up to your CI/CD system. And if it fails, there are unacceptable consequences. You can't just roll back a car update that causes all your cars to crash, because at that point you probably don't have a business anymore. You have restricted code guidelines, like for instance MISRA, where you need to make sure that your code follows certain standards, and not all of these rules can be automated necessarily. You can do a lot of stuff to get close to full validation of MISRA, but you usually have some edge cases that need manual review as well. And there's a lot more. Basically, CI/CD is created for like the web and like these kind of like mobile phone apps, for instance. Things that are like customer-oriented, quite easy to work with. The functional safety is just a completely different domain, where CI/CD It's nice, but you probably can't go all the way. So if you can't go all the way with CI/CD, the question is then, what can you actually use from CI/CD? So if continuous integration might be solving a problem that you don't actually have. Maybe you have a small team, maybe like 3 people or something, and you're constantly in communication with each other. Maybe continuous integration is not solving a problem you have. Continuous deployment is probably not applicable at all, I would say. You probably shouldn't be delivering functional safety updates on a daily basis. And continuous delivery is probably difficult to do as well, because it would require you to basically certify your application constantly, which, depending on your functional safety domain, maybe that's possible, but it depends on what you need to certify, basically, and how this certification looks. So my opinion is that you can still use a lot of this in your functional safety work. The main thing you want to be doing differently is, instead of focusing on what people call CI/CD, like continuous integration, continuous delivery, and so on, you want to be focusing on the core concept of it, which to me is reducing risk. So in a CI/CD pipeline like this one, all these steps are really about reducing risk. Instead of trying to create one big integration at the end, or one big delivery at the end, where you basically can't test anything, and then you have like enormous amounts of crunch at the end of your delivery cycle, you kind of test continuously. And in this way, you reduce risk by making it more likely to find issues early. You make it more likely that you're going to find that you're not going to make mistakes because you're doing this for the first time. Like if you're testing your application once a year, you're less likely to know how to run these tests. You're less likely to know that the tests do what they need to do. Whereas if you do it on a continuous basis, you're going to reduce risk because you've done this a million times before, and you know how these tools operate. So this is a big part of what can be salvaged. Basically, reducing risk by using your automation and making these jobs basically a routine task, rather than a one-off task that happens once every release cycle, which could be years. Another thing is reducing delays. I've seen a lot of projects where once you start getting delayed, quality goes off a cliff, basically, because you no longer you have a lot more stress, you have a lot more pressure to deliver, and you don't want to be delaying things, so people start making mistakes. With CI/CD, you're more likely to figure out where your delays exist. So instead of having a delay that's discovered right at the end of your delivery cycle, you can discover it early on, so that you don't have to stress out a week before you're meant to be releasing, or a week before you're meant to be launching your space station into low Earth or orbit or whatever. And basically the core concept that I want to be bringing is this: if it hurts, do it more often. So continuous integration is meant to solve the problem of integration hell, and that's a pain point. But if you don't have that pain point, maybe you should think about what things hurt in your workflow. What pain points do you have, and focusing on automating these. So if you're using if you're working in the functional safety domain, you might want to be, for instance, automating parts of your certification process. Or maybe you have problems with communication in your system where these different teams don't know what they're doing. Maybe that's where you want to be focusing on adding automation or processes to do those more often. Basically, continuous integration and continuous delivery and so on, they're about taking things that can be difficult and doing them in smaller chunks and doing them more often. And I think this is applicable to functional safety as much as any other domain. Even if functional safety doesn't really allow you to do continuous deployments, possibly, you can still get a lot of gains by reducing risk reducing delays, and basically making things less drama, less likely to cause drama in your work. Right. So that's kind of like what I think you should focus on when you're doing a CI/CD pipeline. I'm still going to call it a CI/CD pipeline, even if you're not going to be doing continuous delivery or even continuous integration, because it's kind of like the way you talk about it these days. But you could just as well call it like release automation or build automation or whatever. It's just kind of like a way to automate your workflows and your processes around development. Yeah, CI/CD pipeline is just ingrained in me, so I can't really go away from saying that. And a pipeline might look something like this. You have a build step. This could be like compiling a linking application. You might run unit tests, where you basically test the parts of your code in isolation. You can do static code analysis, which is basically instead of running your application, you look at the code or you look at the binary that's created by your code and you run analysis there. Like, for instance, you could check like if memory gets tainted at any point or whether you're pulling in some dependency that is not up to your standards. Run integration tests where you test the integration between these different components. So after a unit test, you know that your units follow the specifications that they have. The integration tests are usually where you find a lot of issues, because here you start testing the communication between different teams. So if one team has misunderstood how the contract between two different applications work, integration tests is where you're going to find that. End-to-end tests. Now you're actually deploying it to an actual system. So this could be, for instance, I mean, in web development, it's deploying it to a web server running a similar version of your software as the actual users are running. In functional safety, it might be deploying it to an actual car. Could be any kind of, but basically deploying to an environment that is like your real production environment and running tests there. Usually you want, the issue here is that unit tests are usually quite quick. Integration tests are a little bit slower. End-to-end tests can take a lot of time to work. And then you might build a package, and this might be including all your documentation, might be stuff like, I don't know, instructions for how to install it. All this stuff gets packaged. And then you might even deploy it. And deploying it is releasing it to your end customers with some process. People add things, remove things, whatever, but this is kind of like how a normal CI/CD pipeline might look. And the way they're implemented is you have a source code management system. Git is probably the most common these days, in my experience. But I mean, it doesn't really matter that much which source control system you're using. Git is nice because it has a lot of integrations with a lot of tools. Mercurial is another SCM system that works fine. Subversion, I mean, works fine. There are proprietary source control management systems that also work fine. Basically, all you need to do is be able to hook up to this thing and detect that some change has been made. And that change will then trigger some kind of execution of some form of script. And what handles this change, listening to changes and actually executing scripts, it's done by the CI/CD tool. Jenkins used to be a really popular and big one for a long time. I feel like a lot of people are moving away from Jenkins to, for instance, GitHub Actions or something like GitLab. But in practice, all these tools kind of do the same thing. They listen to an SCM or listen for some kind of event, and then they trigger some kind of pipeline. And then they usually have some tool for reporting the results as well. And then you have a bunch of other tools. For instance, Docker. Docker lets you package your software so that you can integrate to a CI/CD tool easily. Codesonar is, for instance, a static analysis tool that lets you analyze code statically and define the issues like memory issues and so on. Cantata is a unit test in the integration test tool that lets you run these tests in an automated way. And it can also help you do stuff like do code coverage analysis. It can let you generate tests if you need to do that. So basically, the steps to integrating a tool is to package your tool using Docker. This is not something you have to do, but it's something that's going to vastly simplify your work with a CI/CD pipeline, especially with more modern systems like Jenkins. You used to be able to go without Dockerizing your tools, but it creates a lot of issues with like upgrading, license management, creating a new build agents and so on. GitHub Actions, which is probably the one I've used the most, basically needs you to build a Docker image of your tools. And then you define steps. So steps could be something like this, like build, unit tests, code analysis, and so on. Usually it's a matter of like running a bash script or a Python script or something. And then you extract the results. Different CI/CD systems have different tools for this. Usually, this could be in the form of looking at if you have test cases that failed, generating like a SARIF report, for instance, where you can tell what lines have issues if you're running a static code analysis tool. And we'll show an example of it later. And yeah, so Docker is a tool used to package things. And so for instance, here we're packaging this test file in a container with Python. So basically we're taking an existing image, which is a slim version of Python 3. We're copying a test Python file into the Docker image. And then we're saying when this Docker image is executed, it should run Python 3 with the test.py. And this way we can kind of ensure that we have the version of Python that we're expecting, or maybe the whole tool chain that we're using. For instance, if we have like an advanced compiler or something, we can package these in Docker containers so that we know what compiler we're working with. And we don't have issues where like it builds on some machines, but not on others. Docker also gives you reproducible runs because basically you're spinning up a new environment each time you're doing something. You get CI tool integration, stuff like GitHub is built on Docker more or less. You can version tools, so you can try things out with different compilers in a fairly easy way. You'll just kind of specify which Docker image you're using instead of having to like uninstall, reinstall, and so on. And yeah, Docker images for these tools are often provided by the supplier. So for instance, we at Nohau, we have a lot of our tools Dockerized so that we can kind of provide that as a service. But I know that both Cantata and Codesonar come with Docker files or Docker images set up already for you. And then defining steps. It's just a CI pipeline is a bunch of steps that run in sequence or in parallel. And these are basically scripts that are executed inside a container. So if some step fails, the CI/CD system would usually mark the build as failing. This could be if your thing doesn't compile, your build will fail. If your tests aren't passing, your build might fail. If your StaticAnalysis tool finds new issues or issues that are not, but basically I'll have quality gates that say that you can't merge this thing, the CI/CD system will mark the build as failing. And the steps can be defined in different ways. You can use YAML, which is like this, or you can use a script like Bash or Python or whatever. But this kind of basically says that this is a GitHub action step, and basically it says use this action, which more or less checks out your code. And then inside this, we name our step runs Codesonar analysis. And this step, when we want to execute it, we just run this script, which is in your code repository somewhere. And doing this is basically how you build up a CI/CD pipeline, just a bunch of these little steps that together validate the state of your system. And then presenting results, there's a lot of different solutions. You send emails if you want. You could do stuff like just making the logs available. You could create HTML reports. Use Sarif, which I think Rob will show later, which is basically like it's a format for static code analysis tools that can integrate with a lot of CI/CD tools. You can use Markdown to kind of like format your results. With GitHub Actions, you can use pull requests, which it's a convenient place to present all this information. So that when you want to make a change to your main line, GitHub Actions will execute your pipeline, and then it will, inside the same pull request where you're trying to merge something, it will show you if you have any failing test cases or if you have introduced some kind of regression in some other way. This is also where you normally would do something like manual code review, so that all this information gets presented to the person who's doing the manual code review. And then you can have quality gates where you can basically say, like, if we have an issue that fits a certain criteria, then we will stop it so that this change can be merged to the main line. So after this, I'll just show a quick demo of kind of how something like this could look. And it's not going to be a live demo because I have done live demos before, and I don't think they're a good idea. So this is kind of like how we've done it. There's a lot of different ways to do it. Someone's made a change to some code here. They've added a test to the README file, and they've added this printf. So not a massive change, really. And this is a report that gets generated by our system. You can create whatever kind of report you like, really. And it basically just kind of compiles all the results from the different tools we're running. So Codesonar says that we have a bunch of security issues. So this should probably not be, if we had a quality gate here, I would say this should probably not be permitted to be merged. But this could also be like input for a manual code review. If you're running Sarif, it would tell you which lines you've done things badly on here. So for instance, if this printf here has an issue, by importing the Sarif file, it will tell you this line here introduces this issue. So we have static analysis through Codesonar. We do binary analysis as well. And we have QA Misra, which, so this code isn't written according to Misra in any way, which gives us loads of issues. And then Cantata, where we basically run a suite of unit tests. And they tell us that they're all passing, so that's good. And so in this way, we can kind of like collate different tools into a single place, basically. And the pull request is a good place to do it if you're running GitHub Actions. And then, I mean, normally you would have some person would be doing a manual review as well. And if these tools are happy and the manual review is happy, then you can merge your code. And that's more or less how a CI/CD pipeline looks. The steps here are quite simple because we're basically just running a bunch of Python scripts. So like here, we're running a Codesonar script that basically runs Codesonar at the expected. It generates the expected reports. We've analyzed the reports and so on. So basically a bunch of bash scripts or Python scripts that do something. And we execute those automatically each time a pull request is created. And that's more or less everything I have to show. If someone has any questions, I can take them now. Otherwise, I'll probably be around a bit more today.
So I want to talk to you about deploying advanced static analysis in a CI workflow, okay? My name is Rob Daulton, I work for CodeSecure. I've been working with our tool of interest today, Codesonar, for, I don't know, 25 years, something like that, a long time. Seen a lot of changes. and that's one of the things I want to talk about today. Sort of as Sebastian has been talking about, sort of the steady and quickening migration indeed into deploying in CI workflows, okay. So that's the headline of my talk today with a demo. I also want to talk a little bit about Codesonar and its capabilities and features and why advanced static analysis should matter to you guys that are doing embedded software development. So I'll kick off just by defining the use case and then follow up with that demo, fingers crossed, and then a little bit about Codesonar, how it does its work, and some of those capabilities, and quick run round some of those features. Some of you may be Codesonar users, I don't know. Are any of you Codesonar users? Maybe that's not a bad question. Or are you familiar with Codesonar? Okay, all right. You can go to sleep. The use case, certainly when I started 20 odd years ago, most of the prospects that we presented to, they were much smaller teams of guys, much simpler environments. They were all typically a team in one location. As I like to refer to it, it was a guy on a PC with an IDE developing some code with Make. Okay, it was a very simple demonstration and an environment to deploy into. Okay, don't want to belittle that environment. That is still prevalent today. We'll still come across that type of organisation. But most definitely over the last number of years, we've seen quite a strong growth in organisations working in a CI-based environment, okay? Things like the Git labs. As Sebastian said, Jenkins was very popular a number of years ago. There's a few players in this space now. And the need for environments like that is because the code bases are getting bigger, the teams have got bigger, they're geographically dispersed. There's been lots of companies very successful at selling all of your organisations many tools, so you've got lots of tools in your tool chain and they all need integrating together, and CI can nicely, as Sebastian said, bring all of that together. So that's what I want to show you guys today, Codesonar working in that sort of modern workflow environment, which I'll keep interrupting myself just to explain how bits and pieces are working and you know, little advantages and benefits of what you can do in that environment. So I'm no artist, but here's my sort of simplistic view of the world that I'm wanting to talk about. Lots of developers spread around, probably working with some IDE, connecting to some CI environment. There's a whole range of them. I'm not listing everything here. I suppose the key takeaway that comes to mind at this point is that certainly Codesonar can work with any of them. Okay, and it's probably backed by something like Git. That seems to be the common source code repository tool these days. And I want to show you how Codesonar fits into that jigsaw and how the workflow can look, which hopefully it's what you would expect. I'm not going to show you any surprises. So, deep breath. Let's have a little look at let's have a little look at my demo. Okay, so what I have got here is a GitHub repository, and it's got a particular handcrafted, merged together code base of a number of different languages, because Codesonar these days is not just a C and C++ static analysis tool. We've recently introduced supporting other languages as well. A bit more on that later, I guess. And we've got one main branch here, so nothing unexpected. And we've got obviously a pipeline script here, which we'll look at in a moment when I actually kick the build off, and we'll talk about what's going on in there. But the first step ever for any developer is to get probably a clone of that code base into some tool that they're running on their desktop. So I'm picking VS Code today, again, because it seems to be currently the market favourite. You know, for a while it was maybe Visual Studio, or a few years ago Eclipse. These are still IDEs we see out there. We still support them at CodeSecure as well, and a whole host of other tools and so on that might be in your tool chain. But VS Code seems to be the current favourite, so let me work with that. So let me just clone my code base here. So I've got my code base, and we can see all of this is just a replication of obviously the file structure that was in GitHub a moment ago. And the first thing that a developer will probably do is start a new branch to do their work on. Okay, so I'm going to do exactly the same. And I shall call it Nohau, why not? So I'm on my Nohau branch down here, and at this point I can go and be a developer and start working on some code. Now this is one of the points where I'm going to take my life into my own hands, because I'm going to make a code modification which needs to be able to compile, otherwise my demo is going to collapse in a big heap. So I'll call it robleak, and we'll do, I don't know, int x, and let's say, I don't know, if x is greater than 1. If anybody sees any silly mistakes, let me know now. But we've got a new function here, and yeah, I think that should be good. So let me save that. And now you just got to go around the loop of committing and publishing and so on and so forth. Yes. Change. Yeah, lovely. And let's publish that. Okay. So at this point, obviously, my branch has been published to the CI environment, where somebody with authority in that space, who manages the Git, you know, the environment, the code base, whatever their title is, I'm not quite sure. But they'll be responsible for the oversight of that code change on that branch, reviewing it, deciding whether it can be merged into the master branch, so on and so forth. And part of that review process will be to trigger a pull request. Not interested at all in documenting any of this process here. I just want to basically run things through to the point where the pipeline's invoked, okay? And if I click on that there, I can see the output at least of the analysis, or the branch, sorry, the pipeline being executed. And I just want to see this get beyond setup job. Yes. Jesus. Right. I'm just going to have to bring this down a little bit, because I've got a really annoying thing from Teams which gets in the way, and I can't see what's going on. So whilst that's running, let me just take a little look at what's going on in the pipeline script to show you what we needed to do to how Codesonar is integrated, basically. So here's that script that Sebastian was talking about. Is that, hopefully that's, yeah, it looks big enough for us. So as Sebastian said, this is basically just the equivalent of the old make file. You know, it runs through and it builds your code and probably a lot more. It's a bit unfair to say it's an equivalent of a make file, but if you're not familiar with these things, I suppose you can think of it as that way. It's the task which has been triggered to go and compile your code base. So what have we got going on in here? Well, first thing, again, alluding to what Sebastian talked about, is Codesonar's usage of Docker. Lots of advantages to Dockerizing things. People like clean environments, no mess left over after a merge request had completed. They delete everything and then redeploy everything in the pipeline, typically when the next event occurs. So to that end, Docker is a godsend for supporting that mindset, and Codesonar as a tool chain can absolutely be Dockerized. So I've got a Docker container here with all my Codesonar stuff in it. Okay. And then a little further on, we've got the hard work that the merge request performs. So it's a multi-language demo in this case, so there's some C and C++, some Kotlin, some Python, some other bits and pieces in there as well. But the first thing is I run Codesonar here around the compilation of my C and C++ source code, and I'll talk a little bit later just exactly how Codesonar works. But this is Codesonar being introduced to perform some analysis. And then, right, okay. So yeah, there's one invocation of Codesonar for some C and C++ code, and then, excuse me, beneath that I've got some analysis going on of some Python code, some JavaScript code, some Kotlin code. It's a real multi-language demo, okay, just to really highlight Codesonar supports all these things. So when the analysis of all those bits and pieces have completed in the pipeline, there's a step here which basically collects together all of the warnings that was discovered of the analysis of all of those different language directories, and captures it as something called a SARIF file. Now all SARIF is an effort by the static analysis industry, predominantly Microsoft being a large player in there, to standardize the way static analysis results are formatted in files, in result files, okay. And Codesonar, as well as many other tools these days, can ingest or export SARIF format. So we're generating our results as a SARIF file, or collecting our results as a SARIF file here. And then if we scroll a little bit further on down, one particular integration that we have with GitHub, and we have specific particular integrations with different CI tools. We've got something equivalent for GitLab, for example, as to what I'm about to describe here. We'll publish the SARIF findings directly to the GitHub CI tool, so that, as you briefly saw in Sebastian's demo, you can see some of what the analysis tool found directly in the GitHub UI. The idea here with what I'm trying to show you is, although I'm going to break that in the later stage of my demo, is that the Codesonar user interface doesn't need to be the front and center way in which you consume the findings that Codesonar finds, okay? You can have those results in either the GitHub UI, which is very handy for the guy who is overseeing the merge requests, or obviously you can have them in your IDE on your developers' desktops, okay? So having the results where people want to consume them. And then the remainder of what goes on in this script is pushing a summary report again up to the GitHub UI with this particular command line here. So hopefully, yeah, I've not had any red in my pipeline here. So that's all completed. So I should now be able to come over here, and I can see the results in the GitHub UI, at least, of some of that additional integration which I talked about, namely a summary of all of the warnings which were discovered during the analysis. So this particular table is just the ranking of which warnings had the most instances of. So, you know, there's 6 memory leaks there, but there's some Kotlin warnings and there's some JavaScript warnings and so on. And then rather nicely, at least I think, with GitHub, it can look at what the content of the SARIF file is. GitHub's aware of what the code changes were which made up the merge request, and it sort of compares both sources and ends up presenting a nice summary in its own UI of what those changes were, what those problems were in the code edits in here. And through here you can do things like show paths, and you can follow through a nice presentation in here of what's going on. Not as nice as Codesonar's own hub, but certainly as a nice freebie for a CI tool, quite a nice way of reviewing what static analysis found. Something I forgot to talk about in here, but I will mention it now. If I come back to the pipeline script, where is it now? On this particular command line here, yeah, here we go. I take advantage of a feature in Codesonar that allows me to label my analysis basically with the snapshot of the code that it was run against. Obviously, when you're running stuff in CI, you're running lots of stuff, and yet you've got analysis result sets as well. And one of the questions we used to hear is, how do I know which set of Codesonar static analysis results marry up with which version of my code base? Okay, so to address that concern of our users, we added a way of adding arbitrary labels to your Codesonar static analysis results, and literally it can be anything you want. So in this particular case, I added a label which is called the GitHub commit value, and its value is whatever that GitHub commit value is, and we'll see that in a moment. In fact, I'll show you that now. If I just, even though I didn't want to focus on this particular demo of, you know, the Codesonar results interface, if I just briefly go over there, and if I just refresh the view here, here's the analysis I just ran for you guys a few minutes ago, and there's that commit ID which is associated with this analysis. So it can be any information that you want that you choose to attach, but that's just one obvious useful piece of information that you might want to associate with your Codesonar analysis. Okay, so at that point, the guy overseeing the merge request would probably draw their conclusions, perhaps, of the results, and either merge the branch into the master or not. I don't particularly want to do that because I don't want to mess my demo up. But if I go back to VS Code now to sort of complete the cycle, obviously we have some support with Codesonar with the VS Code IDE, but the main support we rely on is Microsoft's own Serif importer. Okay, obviously as Microsoft are one of the key players behind Serif, then a lot of their environments can manipulate Serif files as well, as we just saw with GitHub, which is owned by Microsoft, importing a Serif file. So too with VS Code, if you've got their Serif plugin imported into it. And we've got our own little plugin as well for VS Code, which allows me to go to the VS Code command palette, and I'll see a couple of commands that have been added via our own plugin here, which allows me to either download just the new warnings for a particular analysis or the entire set of warnings. So I'm just going to go for the new warnings here, and in this particular, what our plugin basically does now is reach out to our Codesonar repository and gets an enumeration of all of the different Codesonar projects. I'll define some more of this terminology later. And they're all itemized here, or I can type them in, and I know my particular project that my analysis was associated with is this one. The plugin now reaches out again to all the different sets of analyses that have been conducted against this code base that belong to that project. You can see I've got a whole number of them here, but here we're looking for just the new results to do with my code changes. So that implies comparing two sets of analysis results, the current set with some arbitrary previous. So I'm going to say as my baseline the prior analysis, and the current analysis, the latest analysis, is that one. And the plugin reaches out to GitHub and basically, sorry, not to GitHub, to the Codesonar hub, and requests that Sarif file, which just represents those new warnings due to the code changes. And I have to save that Sarif file somewhere, so I'll save it there. And then we're fully reliant again now on VS Code's own Sarif plugin here now, and it's showing us what's in the Sarif file. And in the locations, we're seeing that there was some problems discovered by StaticAnalysis in second.cpp, which are itemized here. Or we can go from rules and we can see we had a leak or a null pointer dereference in there. And if I click on either of these, as you see I've just done here, then encoded in the Sarif file, what's particularly nice about Sarif is it encodes all of the steps along the execution path through the piece of code that you need to follow sort of key line by key line to understand how this problem manifested in the code modifications that you've made, so that trying to help you to understand what the analysis has found so you can more easily go yes or no. Okay, and I can click on each of these steps, and if you really got good eyesight, you'll see that that caused line 38 to highlight, and then it's telling us obviously that malloc was called on that line. And then I can click on this line here and it says pointer now references the resource of interest, and you can see as I step on each of these statements in this list here that VS Code updates the active line of code, so you can see how these comments correlate, so you can understand what the analysis found and whether, you know, ultimately you as a developer, well, obviously you need to go and fix it, I guess, because it's a bug in this particular case. So, any questions on that before I sort of change tack a little bit?
How well does it integrate with GitLab compared to GitHub?
It's absolutely equivalent to what you've just seen here.
Great.
Well, actually, let me take a step back. So some of that integration into the GitHub or GitLab UI is dependent on your version of GitHub or GitLab. So if you want GitHub, for the maximum level of integration for GitHub, you need GitHub Enterprise. And if you want our maximum level of integration for GitLab, it's GitLab Ultimate, okay? And I almost don't like talking about this subject because people think, oh, well, I might not have got GitLab Ultimate, which means I can't integrate Codesonar. That's not what I'm saying. You can stick invocations of Codesonar in your pipeline script, and you can call other things in that pipeline script to do with Codesonar as much as you want. I'm just talking about the value-added extras of integration into the GitLab or the GitHub native user interface. So we have different tiers of support for different tiers of the tool.
Okay, can I ask you a question? So the Codesonar, I saw that you actually had a Docker. Is it like a single Docker that you actually run into, or do you kind of like include Codesonar into your current build Docker?
I made that Docker container.
Okay.
Yeah, so we've got in our instructions, we've got a Docker file which is about this long. There's only about that many lines that do anything valid. The rest of it is just lots of documentation. Because a deployment of Codesonar is, it can be a couple of gigs. I mean, there's a lot of stuff in code, so manuals and, you know, it's a big piece of stuff and you don't want all that in your Docker container. So a lot of what we document in our Docker file is how to develop or just only contain the necessities. Yeah, I only want to analyze C, so only these bits. So that's why it's such a large thing, but that's what I basically followed our Docker file, and yeah, self-describing help. Anything else? Okay, so you bloody stupid thing. Good. So, a little bit more focused on Codesonar now. Why Codesonar? Why do I think it's a good idea as a static analysis tool? Number of bullet points on here. On another demo I'm going to show you in a minute, I'll show you some of these features and highlight them. But the top one there, the fact that it's configurable and follows a methodology called abstract interpretation, I think is particularly interesting. So C and C++, which is our primary pair of languages which we support with Codesonar, and we apply this methodology of abstract interpretation, which, by the way, we also apply with Java and C# as well, so it's a very thorough mechanism as I'm about to describe. Why should you choose to want a static analysis tool which follows such a methodology? Well, if you think about C and C++, great languages they are, but the truth is, especially C, less so C++, but especially C, you can, as a developer, fall into many traps of undefined behaviour, which is what underpins all of the myriad different types of bug that you can end up coding. You know, your null pointer dereferences, your buffer overruns, uninitialized variables. I mean, the list is humongous, okay? And subsequent languages have come out and learned many of those lessons and developed languages which are memory safe, or have taken a lot of the burden of accuracy and correctness off the developer, and the language automatically makes sure you can't write as buggy code, okay? But C and C++ are still extremely popular languages, and as such, you've still got all these potential pitfalls. So once the first sort of phase of static analysis tools, sort of 3 or 4 decades ago, came out, and it was found that they only really found simplistic type problems, it was realized that tools needed to be developed that could find the primary, more subtle, more high value problems that exist in your code, which are typically to do with all of this undefined behavior that you can fall into. And to be able to develop a tool which can find that those undefined problems, then your analysis engine needs to understand the semantics, the actual meaning of your code, what is going on structurally in your code. And that involves building a number of different models of your code, as you can see in this little pictorial here. Which it might be a bit small, but you know, what are the different types of tokens, whether they're variables or functions or methods, knowing what the control flow graph is through your program code, knowing what the call tree is through your program code. So understanding proper worthwhile information about the relationships and what's going on and the structure of your code, so you can infer the meaning of the behavior of your program. The trouble is, when you've got all of that deep understanding that you've built with all of these alternate representations, the clever guys that started to try to build these advanced static analysis tools realized that there were some unfavorable scenarios that static analysis engines could fall into, such as undecidability problems, basically not being able to fathom whether something was real or not. It was a difficult problem to address. And so one of the ways that was dealt with was by implementing something called abstract interpretation, which is a way of representing the state and the values within your program to be able to overcome some of these problems that I've just described. So it was still a highly accurate method for teasing out real, subtle, complex problems in your code, but it overcame some of the inherent mathematical problems of basically analyses that might run forever, how to circumvent those sort of problems. And finally, you need your analysis tool to be API aware. So you don't typically write your code as sort of a bare metal thing. Obviously some organisations do, where you have 100% of your source code, but minimally most developments will rely on the C library or the C++ library or some other libraries, and you'll have those as a binary only form. Yeah, you don't have all the source code to your standard C library. You just link it, don't you? You call string len, but you just link, okay? But still, a high quality tool needs to be understand what the implications of calling string len or malloc or free or pthread create or a whole host of other common functions that you might call in your code base. Your tool, to be able to be thorough and accurate, needs to understand the meaning of all of those functions as well, so that when your code interacts with these things, your tool doesn't get lost when switching from the code you write into calling malloc and going, I don't know what malloc does. Yeah? So your analysis tool needs to understand all of those functions in the toolkit that you just take advantage of as a matter of course without thinking. So they are sort of the reasons why you really need an advanced static analysis tool if you're trying to find the worthy problems in C and C++. So what sort of characteristics, therefore, should you expect your static analysis tool to be able to do based on those set of arguments, basically? Well, it needs to have a whole program model, okay, so that it can find end-to-end problems. And it's got to be flow sensitive. It's got to understand how data flows along the execution paths in your program. It's got to be, I'm not going to list all these in detail because some of them sort of overlap a little bit, but it's got to be context sensitive. So it's got to be able to differentiate between two different invocations of the same routine based on the arguments passed to the routine and obviously the return value as well. There's a lot of sensitivities that you've got to have. If you don't have all of those capabilities, then as a very rough differentiator, you could say you've got deep SAST versus superficial SAST. And the superficial SAST is probably represented by the family of linters that have been around for years. And actually, without naming names, certainly some commercial offerings as well. But Codesonar certainly falls into the deep SAS category. So if you've just got what I would refer to as a superficially performing SAS tool, then you're only going to be able to find sort of surface level properties, which are single line type problems, okay, easy to spot, easy to appreciate, probably always true because they're quite simple in their nature, but certainly for C and C++, while some of them you might value, they're going to have a low correlation with the real high money problems that can bite you. You know, your concurrency problems, your resource leaks, buffer overruns, security vulnerabilities, which I've not really talked about at all. They're just going to be invisible to that class of tool, okay? And actually to try and help, what am I trying to say here? I don't want to denigrate MISRA, which I'm sure many of you have heard as a coding standard, a safety standard, or an industry coding standard. I mean, you know, we make great efforts to keep abreast at supporting all of the different MISRA standards at CodeSecure. So MISRA 2023 has recently come out for C and C++. And we support those. We've got to. It's a big ask in the community, in the embedded space. Can you do MISRA? So absolutely we can. We know it matters. But MISRA, for many of its rules, falls into that superficial rule set, almost linter type problems. And it's not a guarantee of a high quality code base. It's a starting point, really. That's the best you can get. And there's an interesting study here which I refer to, and I leave for you to go and look up if you're interested. But somebody found that, or some guys found in this study, that only 9 of 72 rules in the MISRA standard were better than random at predicting defects in your program code, okay, which is quite an eye-catching observation, I think. I always remember selling a tool years ago to an organisation where there was a MISRA guy who worked for that company. He was on the MISRA committee, and he sat like this through the whole presentation because, you know, MISRA's all you need was his mindset. But we ended up selling it to them because they did their evaluation and, you know, other things turned up. You know, MISRA is not a certainty. But I, again, fully appreciate that it's a valuable standard that many of our customers care about. MISRA, however, does have some rules in its armoury which do allude to those more gnarly, difficult problems in your code base, the things that I said advanced SaaS needs to exist for. There's one in there in MISRA C 2012, and it'll probably occur in all the other MISRA C standards in some shape or form. Rule 1.3, there shall be no undefined or critical unspecified behaviour. I mean, that's a hell of a rule to go by, bearing in mind what I was just saying about all of the range of undefined behaviour that can exist in C. I mean, that rule is a standard on its own, never mind the other however many rules there are in the entirety of MISRA. And it's for rules such as that which really imply things like the buffer overruns, the memory leaks, and your other high quality classes that worry you when they occur, that you need the deep SAST for. Something that really understands what's going on in your code to find out the things that matter, not the sonar cube type things. If I will name drop one thing because it's a bit of a public domain tool and it's free, so it's popular, but it's more superficial. It's not deep. Okay, so let me, don't know how I'm doing for time here. Somebody,
15 minutes.
oh, that's more than enough. Okay, so let me have a little walk around briefly the Codesonar user interface. So the way Codesonar works is it's a piece of client-server software. The client piece is the analysis engine, the bit you saw embedded in the pipeline basically. We've got different flavours of the client for embedding in your IDEs, for example, if that's how you'd like to drive the experience. And then the server piece of Codesonar is what we call the hub, and the analysis communicates with the hub where all the findings are forwarded to. So when the analysis is over, your IDE will collect the warnings from the hub and show them in your IDE, or as we saw in GitHub, they were shown in the GitHub UI when we got that serif file from the hub, or as I'm doing now, connecting with my browser directly to the hub to look at stuff. Simple organisation, little hierarchy. You've got this idea of a project, which is a particular code base. So we can see some recent code bases that I've worked on here. Immediately below the code base, we have the collection of analyses that you've done of that code base over time. Good reason to hang on to these is the classic, if you're running in a CI environment or some automated environment, you could be shotgunning out those analyses much quicker than you guys can ever review. So we've got them all here so you can go and click into them and look at the results at your leisure when you're ready. And of course there's ways to control the growth of these sets of analysis sets by age or quantity. Going into one of those sets of results, we can see the set of issues which were discovered in that analysis, easy to understand table, type of problem, the file it occurred in, the line number, the routine, and some triage information over here, which we'll talk about in a moment. But if I dive into one of these issues, one of the great strengths of Codesonar is, and we saw it a little bit with the annotation in VS Code, but I think it's even more nicely presented in our native interface, is how we decorate the piece of code where we found the problem with commentary, so that hopefully you can follow that commentary and quickly understand and draw your own conclusions whether this is a real issue or not, basically. It's a really simple issue, this one, but it picks on some nice capabilities I like to touch on. This is our terse commentary, which is normally sufficient with a little bit of experience for you to understand what the tool's trying to tell you. But if it's not, you can typically click on the All Events link, as I've just done there, to give you some more verbose, almost line by line sometimes, commentary about what the analysis thought was going on here and here and here and here. And so if I step through this reasonably quickly, Codesonar is saying, hey, you've called a recognised allocator here and assigned its return to this pointer variable here. And then you pass off that pointer to string copy. And this is one of those things I talked about earlier, that API sensitivity. I don't have the source code for string copy, just linked against it, as you appreciate. But because Codesonar knows about the behavior of the string copy function and hundreds of others, yeah, this is a simple example, but hundreds of standard library functions that you may rely on in your day-to-day work in C and C++. But because Codesonar knows about the behavior of string copy, it knows in this case that string copy, if you can read that, had no really important impact in this case on the state of the variable, which is clearly at the center of this particular problem. And then our variable pointer is passed off to another routine, go and use, where it becomes another variable. So again, highlighting how, you know, the analysis is aware of the data flow and you know, through the call tree. And then we've got here a simple if condition. And in the particular case where the analysis takes the false branch, and Codesonar will have pruned out all of the infeasible paths of execution during its analysis. So what do I mean? What do I mean by that? If I had a piece of code that said x equals 1, and then I had a statement after that said if x is 1, do this, else do that, Codesonar wouldn't analyse the else path through that if statement, because it knows x is 1, it's seen x is 1, it's tracked that x is 1, or it's tracked the value of the pointer, or whatever is involved in that conditional expression to the if statement. It evaluates it, and if it realises that particular path is infeasible, doesn't waste its time trying to find problems in paths that can't be executed. Okay. So in this particular case where the analysis took the false path through the if statement, and you see the easy problem here. I remember to free in the true path, but I've forgotten the false path, okay? But believe me, if this piece of code was spread over 2 files and 500 lines of code, I'd be, and I mean, nearly willing to put money on it. You wouldn't find this with a manual inspection. It's just that it's because it's in 10 lines of code. But this is an easy problem, but easy problems can become hard to find when they're, as I say, spanned through a call tree. And so you follow the rest of the commentary and you get a concluding event which says, basically because of everything I've said up to this point, therefore there is a resource leak in this particular case. Down here you will notice, hang on, let me just go here. Down here we can scroll to the bottom where we can apply some triage, some status to the issue. Was it real? Was it false? What's its priority? Who owns it? Things like that. Some comments that you might, oh yeah, you know, why you believed it was real. All that good sort of stuff. And then save that information away with this issue in our repository. Some of our IDEs also support being able to do this level of triage in those environments as well, if you're reviewing warnings in IDEs. If I come back to the results here, where was I? Let me go back. It's jumped me around a little bit. Here we go. Let's come back here. So, these are the results that I got earlier. It's a different code base, don't worry about it. But we'll see that many of the results here have already got a triage status, a priority, a state, whether they were true, assigned to me. This is one of my demo code bases. I never fix any of these warnings, otherwise I'd have a boring demo. So these problems, every time I run the analysis, they're always rediscovered, okay? But the nice thing is, Codesonar not only rediscovers the same problems, which you'd hope it would, but any that are recurring, whatever triage status you gave to them in some past review of this code base, will be maintained for the latest instance of that problem in the current analysis. So in other words, if I literally had run the analysis of this code base 10 minutes ago, all of these warnings that are assigned to me, which I hadn't fixed since the current analysis, will still be earmarked as pending and trues owned by me. So in other words, I can focus my attention on the issues that I appear not to have reviewed because their triage status is still sort of non, for example. But even if you have only ever had a cursory look at your warnings and not bothered to start to formally assign status to issues, we've got some nice ways of segmenting the results in Codesonar, such as, please Codesonar, just show me the new warnings in this analysis compared to all the previous warnings in this for this particular code base. And for the reasons given already, I never change my demo code base. I never have any new warnings. But what you guys would see in a real environment would be the small subset of warnings that are to do with your code changes. Yeah. So whereas analysis 1, if you turn on MISRA in a mature code base, might find 10,000 problems and you want to kill yourself. If you run analysis 2 after you guys have all the same gone and made some code modifications, still with MISRA turned on for analysis 2, but in analysis 2 selected this new filter, instead of being shown those 10,000 warnings still that no one's got round to fixing, you might be shown 20 warnings. And they're the ones that you can focus on, yeah, a more manageable set of warnings to deal with. There's other features in here as well, such as being able to compare arbitrary result sets as well, such as compare this analysis with my baseline analysis, which I sort of alluded to in my CI workflow demo. I think I might be almost at the end. I wrote down a couple of things. I just wanted to make sure. Yeah. It goes without saying that we can generate a whole host of reports to support these things. So for all the various different standards we support, MISRA and CERT and OWASP and SANS and plenty of others, we've got corresponding reports that you can rely on, or if you fancy edit the structure of those reports, we've got a report builder which is a bit like a drag and drop graphical editor in a way. I won't go into it now because I'm getting short of time. A whole host of other features, but you know, I'm aware I've been talking a long time now. I can feel my voice starting to go. So if I just flick back to my presentation, I have almost finished, but one sort of final point I do want to make is there are a lot of tools out there all the same, even though I think Codesonar is good at what it does. You know, if you search for name me a static analysis tool on Google, you'll get pages and pages and pages and pages of them. And you know, it can be very difficult to try and distinguish between all of these tools. So one of the things we're quite proud of at CodeSecure that we want to make more of, to be honest, is our what's it stand for? Our Net Promoter Score, which is an industry metric to try and gauge what quality of organisation you are when it comes to supporting your customers. Okay, and there's some metrics over here in this table on the right which give sort of average scores for different industry sectors. But obviously the point why I'm bothering to put this slide up is that, you know, we score extremely highly as a support organisation. So we don't just support you or our partners, of course, during your evaluation and then say thank you and goodbye. You know, we're there all the time. We'll help you during the evaluation. We'll help you deploy during and after the evaluation. You know, getting that CI integration set up, for example. It's not a straightforward system, as Sebastian alluded to by having screenshots rather than a live demo, you know, will help you with these things and make sure that you get out of the tool what you want, and make sure your experience is good. So, thank you for that. I hope that was interesting. Any final questions?
Yeah, I have a question. We talk about call trees, and I've tried to use stuff like Doxygen and stuff like that. And Doxygen sort of falls on its back when the moment you have a function pointer in a callback function or in a state machine and stuff like that. How do you handle that? Are you able to find the real call tree at runtime?
Yeah, we're not in the Doxygen's not in the same sort of league as Codesonar for being able to marry up the tokens and know what pointers align with function pointers, for example. Yeah, so I mean we'll trace through function pointer calls as part of a regular call tree. Yeah, so you allocate here, you call a function through a function pointer which does or doesn't deallocate, and find the corresponding problem if one exists.
Good. Just trying to formulate the issue. I realize there's a difference.
None of these tools are perfect. Yeah, there's always going to be false positives for a number of reasons. But I mean, Codesonar's been around for 30 odd years. It started off at Cornell University as a research project, so it's got a really strong heritage, and a lot of intelligence has gone into it now over a lot of years. A lot of the guys that were involved probably wrote some of the book at least on what a static analysis tool should look like.
Hi, good morning everybody. My name is Matt Davis. I'm the Managing Director of QA Systems in the UK. I have been with the Cantata technology for a very long time. I got my notification on my HR system that today is my 33rd anniversary of working with the company. So I've been here a long way. So I'm going to talk today about efficient unit and integration testing of safety critical code. Not all of you will be developing safety critical code. There are some lessons that you can learn from the application of safety critical code. What do I mean by safety critical code? Those types of industries. So I'm also going to touch on how our Cantata solution differs and goes beyond the basic xUnit framework set of tools. So my first question, audience participation time, who has used a unit testing tool before? Who's used an xUnit framework testing tool before? Okay, so some have, some haven't. Okay, good. So a couple of definitions just to start out. This is the terrible Wikipedia definition of unit testing, a piece of individual source code fit for use. What it actually means in terms of testing is verifying that unit as an executable, i.e. dynamically running it. So this is different from the static analysis, looking at code statically, but exercising that code in a dynamic environment, whether that's host or target. Principal purpose of unit testing is the correct internal processing and the correct uses of interfaces of that unit to other things. By contrast, the integration testing definition in Wikipedia, what we're looking at really here is a cluster, again verified as an executable, but principally not looking at the internals of each unit, but looking at the interaction between them. So cluster verified as an executable, inter-unit memory allocation, order of calls, data manipulation, etc. Something is trying to call me, so apologies for the background noise. Okay, unit isolation testing. What you might do, very, very simplistic style system. Lots of units, global data. Where might I start? How might I approach this? Well, one technique is top down. So you take your parents' unit A and you use that and test the subunits simulated and then calling them as subunits. Different approach, bottom up. The test script drives the child units, and then these units are used as validated or verified inputs to unit E in high level tests. The third option is test them all as one. So test them as a big integration object. Don't individualize, don't isolation individual units, but test all of the interactions of the units as they go. This is very annoying, isn't it? Fingers crossed somebody will stop calling me. Integration testing. What does that mean? It means taking the units as a cluster and testing them with a script driving at some point. What does that mean? As an integration script, it means multiple units built as a single executable, not individual units as individual executables, with the test script acting as a driver. You may have other libraries or other code involved, so third-party libraries, it might be a boost, it might be an STL, for example, and you're building a test executable. In this circumstance, you are looking at potentially not having all of the code implemented, or where you are implementing the code, wanting to test the interactions. So you have a choice between simulating items that are not complete, or intercepting and using items that are complete, with a choice of driver entry. So you can choose where in your stack of code you're actually going to start invocation. There's usually no scalability limit for integration testing. There is, however, one big limit, and that's up here, the complexity of what's going on. So this system is not very big. Yeah? If I've got 10,000 units, that's bigger than comprehension very easy in a test. So scalability becomes a matter of understanding what is supposed to go on. And normally with forms of integration testing, and I'm differentiating that from a system test, because you are looking at full unit test capabilities for a script-driven integration test environment. So similarly with Cantata, it doesn't matter if your unit is a single source file with 10 functions, a single source file with 1 function, or 100 source files with 10,000 functions. There is no scalability limit. You can do all the things you can at a unit test, at an integration test. It is just the comprehension of what's supposed to be going on. What do I mean by safety critical code? Well, these industries, illustrated by these graphics, map to these various standards. Virtually all of them are derived from the generic standard IEC 61508, which is often used for general industrial electronics and automation, probably the most one suitable for the guys in the room. But everything from cars through to nuclear power category A control systems, where you really don't want things to go wrong. What it means by safety critical is if the code goes wrong, it either hurts people or kills people. Okay? So, if we're looking at testing in the software development lifecycle, what does that mean? First thing it means is you've got some code, but you don't just magically have code. Yes, you define your code from something as a set of requirements. Now, what level of decomposition you do at each stage, adding more detail from your software to your system requirement, to your software requirements, down to individual items and components, potentially even individual units. You will also find there is a degree of decomposition directly into code. Why? Because people don't write down in requirement specs every single thing that a piece of code should do. Defensive programming, system setup, initialization, these are very common degrees of additional decomposition. The verification order on the right-hand side of the V starts with nothing to do with any of these requirements. It starts with static analysis. The first type of static analysis you might want to do is, does it meet a quality standard? Now, what is your quality standard? It might be as simple as MISRA coding standard. It might be more complex. I want a number of security approaches to apply. I want to look for bugs in advance of spending my time using a testing tool to dynamically verify behavior. Why? Because it's faster. Static analysis tools are great. You run them on the code, they tell you what could be wrong, you can go and fix that before spending any time writing any tests to try and prove it goes wrong. So that's the thing you do first. The first type of testing is, does the code do what it should? What does that mean? It means functional requirements-based testing and non-functional requirements-based testing. And that can occur at any of these levels, right from down at a unit, right through to a system level. Some of them will be different, depending on the nature. So non-functional requirements testing is quite often done at a higher level. These are things like, does it perform at speed? Does it perform with a suitable user interface? Is the user experience good? It might be various other non-functional requirements. But beyond that is, does it not do what it should not do? Does it not go wrong? Yeah. Static analysis will tell you some of those possibilities, but there are lots of others as well. Does it not do what it should not do? That's a form of robustness testing. Please do not test your code with a hammer. That's just an indication to show the idea. The whole concept here is, how hard can I push? In all of the software safety standards, they will dictate that you do some type of robustness testing. This is the one area of testing which is potentially infinite. Don't do infinite testing, you'll never release your code base. You might want to do full requirements-based testing. Does it do everything it should do? Yeah, functionally and non-functionally. But can it not do everything it should not do? May require the infinite possibilities of variations and variables and the amount of computing power that becomes uneconomic to do. So you make a judgment call about what level of robustness testing to do. One element that helps you indicate how much of that should be done is structural code coverage. It is a very common technique mandated by all of the safety critical standards that says, almost as a backstop, after you've done, does it do what it should? Does it not do what it should not, to a reasonable degree? Have I tested all the code? Have I got code here that I haven't got a requirement for? Why is it there? Has it been copied and pasted from some other branch? Is it doing something it should not do and I haven't verified that it shouldn't do it? So structural code coverage for all of the safety standards is a backstop that says, have I tested enough? In other words, is all the code tested with either a functional or a robustness test, and should it be there? The different testing methods, colored by different colors, as you saw on the previous diagram, are listed according to the different standards here. They vary a tiny bit by what's called SIL, or Safety Integrity Level. Each one of these safety standards has various levels. Is it really going to kill people? Does it matter so much? Is it just the color of the indicator on the steering column, or is it something that's going to control the engine control unit in a vehicle and stop it crashing? There are differences, yeah? But nonetheless, these basic techniques across all of these different standards are listed here. As you can see, lots of different types of robustness testing, like error guessing, fault injection, and so on. So, turning to xUnit tools, what are they? Well, they come from Smalltalk's SUnit design, long time ago, 1998, after I started selling Cantata, which is a more commonly known as the JUnit framework, because JUnit followed SUnit. So, xUnit framework shares some basic concepts: a runner, some cases, test fixtures, the big core bit of it, which is assertions, assert that this is that, a test execution, and test results formatter, taking the input and providing some form of result. The frameworks are almost always available as a portable library. So it's not a full testing tool, it's a library that you can pull in from a script or a suite, whatever terminology you want to use. And very importantly, they're open source. They come with open source licensing. That means they are free to acquire. This is not quite the same as free to use, because there's cost associated with using something limited. Also comes with community level support, so you don't have a commercial vendor behind the application. I'm going to contrast a little between the two, Cantata as a commercial level tool for unit and integration testing, fully certified to all of the different safety standards, right up to the highest safety integrity level. And why? Because of test efficiency. I'll come on to the certification right at the end. And that efficiency is driven by automation. An xUnit framework providing you a library is basically a cookbook. I can go and write some code to test some code using a library with a number of basic assertion functions. So, what are these efficiencies beyond the xUnit tool limitations? The first, and by far the most important, is manual test creation. If you are typing your code, and you are typing all of your tests in a code-based framework like an xUnit tool, you're doing a lot of typing. Yes, you have code completion, yes, you have library functions, but nonetheless you are still writing an awful lot of code. By contrast, Cantata as a commercial tool can offer a capability which automatically generates tests for you. As Henrik said right at the beginning of the day, one of the most expensive things in developing embedded software is writing unit tests. If you can have a tool that automates the production of those, it becomes much more efficient. The second one is a stylistic thing. I think this is driven partly by the TDD community, it's partly driven by the nature of the xUnit framework tools. They tend to be black box. So you are taking a function and you're calling it through its public interface, and whatever static functions or private methods are associated with that public API are blind to the test tool. You call through the public API. Why is that limiting? Why is that a less efficient way? Because controlling all of the behavior in that stuff that is static, private, protected is easier with white box testing, where you can intrusively poke the software at that level. Why might you want to do that? Simply, good example, I've got some condition. When this is the 25th time that this function is called, what do? It does something different. Well, I can go in immediately and set it at the 24th, call it one time, that's faster. It's white box testing, it's just more efficient. I'll come on to details. Mock simulations. Does anybody here not know what a mock, a dummy, a stub, a fake, or anything like that is? Good, so we're on the right page. There are some limitations to the way simulations work when you are doing unit and integration testing. I will touch on a very powerful, unique capability in Cantata called wrapping, which provides the ability to intercept, not just to simulate. And then there's limited error injection, where you have a basic black box framework and you are driving your software through that with an xUnit tool, you get limited error injection. And I'll touch on a capability we have in Cantata called custom code injection, which goes beyond even what you can do with wrapping to directly inject errors anywhere in the code in a controlled way. And finally, there's lack of tool certification. I mentioned xUnit frameworks are open source. They're not certified. I'll come on to that right at the end. Cantata is fully certified to all the highest levels of tools. And we have just launched a new product called Cantata Hybrid, which I think you've got some information in your pack about. Has anybody here used Google Test? Quite a few, okay. It's a very, very popular xUnit framework tool. It has one major limitation. It's not certified for safety critical use. Okay, so I touched on automatic test case generation. Why do we use it? Because it's hard work not to. It's as simple as that. Even with powerful authoring tools, Cantata has lots of capabilities to help you design and create test cases very efficiently from a test framework, saying, I want it to do this. And it will go off and create that. It will understand the code. It will use all of the hooks. It'll say, which functions do you want to test? How do you want to test them? Blah, blah, blah. But even with that, which is more than is available in an xUnit framework tool, it takes a lot of effort to write all of this stuff because you're typing a lot of code tests. More importantly and more challengingly is insufficiently validated requirements to test against. Does the code do what it should do? Do I know what it should do? Did anybody write it down? Did they put it in a comment which they didn't update when they changed the code? There are lots of challenges here with insufficiently validated requirements. Are they correctly decomposed, correct, complete, unambiguous, logically consistent? All of those things. I mentioned design decomposition. Even when you have a really detailed spec of what the function should do, some engineer's going to go and type in some defensive program. Ooh, what happens if I run out of memory? What happens if this happens? High reliance on structural code coverage and reverse engineering becomes the result. So you have a load of tests, you've got some code, I've tested everything it's supposed to do, and I haven't tested all the code. So what do? I look at which bit of code is not tested, and I write a test for that bit of code. That's reverse engineering. You are basically testing the code does what the code does because the code is there, and you write a test just to achieve the structural code coverage. It's not a good technique, but a lot of people do it. It's a challenge. The complexity of test vectors. Okay, it's great when your code is simple. If it's greater than 10, do this. If it's less than 10, do that. If you've got a combinatorial effect of lots of different parameters or data affecting the outcome or behavior of your functions, you are looking at things like setting up the preconditions, the inputs, the expected outputs, the order of calls you wish, and the postconditions. Sometimes it is difficult to create the edge conditions for white box testing with hard-to-reach parts of code. I'm not sure which combination of values will give me the output I want. Efficient test case selection. Am I using boundary value analysis? Am I using equivalence classes? Does everybody understand what an equivalence class is? It's basically the same thing as an expected behavior from a variable holding multiple values. So if it can be greater than 10, it could be 10, it could be 11, 12, 13, all right, up to max int, whatever. Those are all the same equivalence class because they're greater than 10. But they're not 10, and they're not less than 10. So those are 3 equivalence classes of positive integers. So, weigh up the benefits of potentially automatic test case generation. I'm not going to touch, because we haven't got time today, on the alternative, which is generating test cases from requirements. I can tell you we're doing an awful lot of research at the moment in the AI sphere on large language models, on reading requirements and generating test cases automatically. That's not an uncommon thing for a test tool vendor. Watch this space for the roadmap. However, we can generate test cases from code. Why? Because you have code. You have to have code to be able to do the dynamic tests. Your code should be an implementation of your requirements. Somebody's gone and said, it should do this, I will write some code to do this. If you've got code that is meeting your requirements, you can use test vector generation using path solving algorithms and intelligent optimization to create tests for each one of those requirements outputs. If you've got a full test framework, which Cantata is, it allows you to define all the preconditions, inputs, expected behavior through the function, and expected outputs and post conditions. Tests can be generated so they're maintainable and readable in a structured format. They are in Cantata in standard C or C++. And we do this with our functionality called autotest. So we read the code and we generate test cases from the code. Where's the brain come in? There's always a brain. Okay? You can't do everything automatically. The brain comes in. Does the generated test verify the requirement? Why is that a good loop? Why is the closing of that loop important? Because if you've got code that is not implementing the requirement, the test will create a passing test for that code. And if the test says it does X when it's greater than 10, and actually the requirement says it should do Y when it's greater than 10, the code is wrong. So the auto-generation of the test and that linking, that brain thinking, has elicited the failure. How do we do it? We generate a script. You read lots of Cantata options, what coverage you want, whether it's call interface control, interceptions, simulations, black box, white box, OO style testing, algorithmic based auto testing, etc. With those options, we read your code, we parse it. Parsing is an essential element of a powerful testing tool that basically tells us what's in your code. It's a bit like the models that we were referring to with static analysis earlier. We do a Cantata static information file for every source file under test. You can select them on a command line or the GUI. When you're running with your auto test algorithm, that pulls in those things and generates 3 different outcomes. Makefiles to build your tests, test scripts containing the test cases, and an auto-generation report, which tells you what you should get. This is it in more detail for the test vector generation process. Start with the source code parse. We use a node graph representation of that. We correlate that with in a test case generator, setting and pulling in the options. So if you want to achieve all the decision outcomes in your code, you ask it to achieve all the decision outcomes. If you wanted to do modified condition decision coverage, the highest safety critical level, you ask it to do that, and you often do it. It uses a combination of an AST, abstract syntax tree, alongside the node graph, and then it uses a combination of a SMT path solver, Gaussian elimination, and generates a number of potential test cases through the code. What does that mean? It's got the path tree. In this case, very simply, 3 different paths through the code, different branches. Are they sufficient? Yes. In which case, it goes off and uses an optimizer inbuilt. I'm not going to generate tons of test cases. I'm not going to bash the code. I'm doing a pinpoint path through the code with each different test vector. So each one's a delta. I then end up with my 3 test cases, and they go into a driver script, and the script and makefiles and the auto-generation report. So considering the paradigm where we are, we've got embedded software, got some software under test up there on the top left. It might call other functions, might call operating system functions, might interact with the target. These are all things that are in scope. So the defined inputs for those are everything to do with the function parameters, the accessible data, the preconditions, the system initialization, etc. The expected behavior is what calls are made by functions, what data is written to and read from, what interrupts are handled from the code as it runs, and the expected outputs are things like function returns, accessible data changes, and of course, the code coverage achieved by those tests. So the driver sets that stuff, calls the software under test, defines the inputs and the expected behaviors and expected outputs. The whole point about dynamic testing is, does it do what it should do, what you expect it to do? So you define what you expect and you check and compare that to the actual behavior. So the control of interfaces, everything from simulation and interception, checking the call order. And that might be that one function is intercepted inside the same source file, so it's within the compilation unit boundary of the software under test. It might be going outside to third-party software, which you don't have access to, but you are going to intercept it and check what it does. Same with an OS or compiler library, for example. You might want to simulate or intercept with the physical hardware, so firmware messages or hardware interrupts. An automatic generation creates all the simulated calls, all the interceptions, and calls with wrappers or stubs. Here's an example. We took this is actually from telecom code, originally from Orange, if I remember right. Simple C source code, 541 source files, 807 functions, basically the big numbers. 55,000 lines of executable code. We used our own tool to measure the McCabe cyclomatic complexity, which gives you a really good approximation of the number of decision outcomes in that code. 4,900. It took 2 hours to generate the tests, 36 minutes to execute them. It's now a lot faster than this. We did this a few years ago. Very high levels of code coverage, but more importantly, 4,900 outcomes, 5,035 test cases. Very close to optimal set of test cases for that entire code base. And the depth, 55,000 lines of code, nearly 6 checks per line of code. What are we checking? Everything. The state of data, the state of calls, what's parameters passed backwards, returned backwards, and so on. You don't have to go to that level of detail, but that shows you if you do, it is doable. Okay, use cases in safety critical code. The first one is you get a report on generation. Is your source code actually testable? Are there things that are dynamically unreachable? Is there data uninitialized or functions that are static or data that's initialized in functions that are static? Does it create a crash scenario? We don't want a test that's just going to crash. The whole point is that this is not a robustness test. It's a test to prove that the code does what it should do with path solving. So those are some limitations that it will fire up. Test cases can be assigned as requirements-based tests. I'm going to come on to this in a little bit more detail, but you can generate tests and they can be reviewed and used, unaltered or modified, to meet requirements-based verification objectives. Some standards, nobody working in avionics here? Good, you're fortunate. Some standards like DO178C, the avionics standard, says every single test case, no matter how or why it is used, has to be traced as a requirement-based test. You must define a requirement for every single test case. Targeted test case generation. You may already have a load of tests from your system test. You're just trying to plug some gaps in the testing with your unit test. You may already have some unit tests and you want to plug the gaps that you don't know how to get the different combinations of data for. Targeted test case generation is particularly powerful when it comes to complicated metrics like decision coverage and MCDC coverage to help with all those different combinations of boundary values. A couple of little diagrams just to show this is the avionics standard, all require verification of low-level or mid-level integration requirements. So you can see here complies with unit design and fulfills the architecture in the software. This is for automotive, 62304 in the medical space, same sort of thing. Demonstrates traceability between requirements and different levels of tests. So, how do we do the efficient tracing and why? Well, the first thing is why is because if I'm generating tests from code, and I need to say, is that test a valid verification of the requirement? I need to know what the requirements are. I need to be able to link them. Yeah? If I'm going to have all the tests, the tests are proving that all of the code is tested to show that it does what it should, I need to know what the list is of what it should. Okay? So, how do we do it in Cantata? We import it. By the way, there's nothing for this in xUnit tools. All right? They just don't have the framework for it. Bidirectional requirements traceability. We import requirements from a requirements management tool or ALM tool. Yep, that could be a powerful one like Doors or Codebeamer or Integrity or Polarian, etc. Or it could be like what most people use, Excel, because it's on your desktop and it's cheap. Yep, and you can do pivot tables. So we can import the requirements in 3 formats: CSV, Excel, or something called RecIF, the requirements interchange format, which is an XML, specialized XML for requirements tools. Gives you lots of extra data. Cantata, you have a drag and drop interface, so you can see the requirements inside the Cantata tool, compare them to the test that's verifying that requirement, and say, yep, link. What does that look like? Looks like this. This one's very flat because it's Excel, so I've got a system set of requirements. For example, when system valid returns OK, check status, global data int shall be set to OK. Yep. Set of requirements, set of tests. Take a test, drag it across to the requirement, and it's added and assigned. This one is an auto-test generated test. So this test case on the left is created to solve the true case of average B greater than 18.25 at line number 35. Auto-test helps you do this by giving you that level of detail. Why was this test vector different from any other? The explanation and the location. And because of that explanation and location, I can very easily map that to the requirement. This works well when your low-level requirements are nice and detailed. The less detailed your requirements, the harder requirements traceability is. This function should do the right thing. It's not a good requirement. Yep, you can write some tests for it, and you can link them all to that requirement, but it's not easy to make the correct calculation. So, drag and drop, auto-test, path-solving description aid the linking, whether it's a test case or a test script. And a controlled export contains all of that link, passes it back to the requirements management tool, or Excel, so another tab in Excel, for example, or updated tab, with all of the data and the code coverage achieved and the status of the test. That gives you in the one thing that you control, your full bidirectional traceability. The reason we don't do it inside Cantata and keep it in Cantata is, what do you trace your requirements to? Tests, but everything else. Yeah? Review records, contracts, source code items, third-party libraries, the whole lot. So, you keep it in your repository, we help you by providing a link. It aids. Traceability helps you identify gaps in requirements-based tests. I've now got some code. I've got a test for it because my auto-test generated a test. It doesn't link to any requirements. I've got some code doing something. I haven't a clue why it's there. Yep, I either decide to write a requirement for it or get rid of the piece of code. I can identify gaps, overlaps, and duplications. It gives me the visibility with a traceability matrix, and it supports requirements coverage as well as code coverage and test coverage. Unfortunately, never things stay the same, so your requirements change. Who in this room has had a set of requirements for an application that has never changed?
What is a requirement?
A requirement is,
No, I'm just kidding.
a requirement could be anything. Honestly, it could be a JIRA bug report, fix this. Yeah, but everybody has changing requirements. So,
I'm just kidding about the requirement.
of course, my issue here is requirements change, they're going to impact your tests if they're requirements-based tests. So Cantata also, in its Cantata trace capability, allows you to identify new, changed, and deleted requirements. As you can see here, there's special filters that allow you to say this set of requirements varies by what. The more data you have in the information you pass into Cantata, the more information it can present to you. So you can focus on what has changed for testing. You can handle versions and variants of requirements for traceability. Unfortunately, it's not just requirements that change, it's also your code that changes. So when it comes to test maintenance, Cantata has an impact analysis and change-based testing approach to the way in which it looks at this. For easier test maintenance, it basically stores the last state of the software under test, compares it to the current state, and you can run and identify the impacted tests and changes. And what? Well, all of those different things. So if a function or a method, for example, has been added or removed, the signature, either its scope, return type, name, or individual parameters, any of that has changed, it'll be an impacted test. So it identifies specific changes for you. This has changed. My variable new static data has been added to the file. What do I want to do with it? They're all hyperlinked to a code editor, and it gives you suggested options. So do I want to add that piece of variable to my test? Yep. Okay, moving on to another capability area that is different from xUnit. Talked about black box and white box. With black box tests, you might want to do every single test as a standalone test, or you might want to do it parameterized. Google Test, for example, has lots of looping parameterized tests, a sort of table-driven approach. We have the same inside Cantata, particularly good for robustness testing. You're going to bash lots of values at it rather than just one. It's a more efficient way of doing it. But also you might want to put tests inside encapsulated code, so private or static data, for example. The little graphic basically gives you the description, black box, white box, sometimes known as clear box, because you're going inside and controlling the internals. So where Cantata is providing power and precision on table-driven tests using multiple values for parameters or data inputs, user can define selected or predefined looping tests and import and export that data via CSV. All available in the interface. Automated accessibility instrumentation means it will call private methods and static functions directly to be able to set and check data, particularly good for trigger values. Put it in the state precondition, give it an injection, do it something, see what happens. Is it the right thing? You can also use interception and simulation of calls within the compiled object. That means interception. I will come on to that next. If you've got an isolation unit test on the left-hand side, you've got script, you've got function, it might call things. You might want to do different stuff with it. Very commonly, I've got my mouse. Is it working? It's not coming on screen. Function B over there on the left-hand side, I'll use my finger. That's a standard simulation. That's where your dummy, your mock, your fake, your simulation comes in. If you're within your compilation boundary, so you're compiling functions A, B, C, D all together in the same unit, it's much harder to simulate, mock an object that is already in the compilation boundary because you have duplicate references. For an integration test, that problem just explodes. Okay? The more you put inside your compilation unit boundary, the more you are dealing with the thing that is integrated. And why would you simulate something you want to actually use to test it does the real thing? So automatic generation in Cantata gives you the stub simulation and the wrapper interceptions, depending on the type of call that's being made and where the call is within the compilation unit boundary or outside it. But not only that, inside each one are programmable instances so you can do different things on different occasions. And efficiently, you can reuse those across multiple tests. So you can have certain tests that say, do this and just behave as normal. I know I'm calling malloc, yeah, and I just want it to run as normal. But in one test case, I want not to use malloc. In normal, I want to inject an error. I've run out of memory, and therefore I'm going to trigger something to be the return. You can have very flexible call sequences. You can have one per test case. You can have multiple interleaved parallel call sequences. It's very complex and powerful. This is a nice, simple way of just showing it. When I simulate, I have a stub, and it replaces the object at link time. And isolate is a specialized form of wrapper, and it replaces specific calls at runtime. I don't use it. I simulate it, but I can check, and I can push things back. Yep. This is my mock object. If I'm going to intercept calls, I can have a before-after or a before-replace pairing, and I'm intercepting those calls at runtime. Cantata creates wrappers. You can do exactly the same as you can with a mock simulation. Check things on the way out. But you can also modify things to this real thing. Now, it might not be change anything into it. It might not be changing a parameter. It might be changing another precondition, such as a piece of global data. You might want to flip a hardware register at this point, see what happens with this code. But this is the most powerful one. You can check. If you're doing a simulation, you are basically testing your source code when you say this called object does X. And you are assuming the source code, this thing over here, does X. If it's not your code, it might not do X. So you can actually check it at this point, as well as set and check other post conditions, and modify returns and parameters of that to the source code. This is the standard before after. It's created by default, and it doesn't force you to check anything if you don't want to. But it provides you a hook to be able to. But it also allows you to do the replace. On any individual call from function in your source code to something else, that called object can be anything, third-party library, database, Java code, something else, you can simulate it. So you can choose, use it or simulate it on any single call. Main advantages for this integration testing, you can check rather than guess. Test scenarios based on a simulation that is false are not a good test scenario. Yeah? I assume it will do X, but it doesn't actually do X, it does something else. I retain all the control of isolation testing when I get to integration testing. So you can set up test preconditions faster with white box access, and you can inject errors at this call boundary. So when the call happens, you have control again. Normally with a test framework, you call the function, it goes off and does its thing, and you check that it did its thing. Here, when a call happens, you get control again as the tester. So every function call gives you that opportunity to control. That's first off. You can scale it up to integrated software, and it can test with hardware in the loop, software in the loop. You can simulate hardware failures very easily with wrapping. It's a particularly powerful scenario for it. But beyond that, we can do custom code injections because you only have control at the call boundary with wrapping. You might want more fine-grained test control. Cantata custom code injection allows you to put it on any statement, anywhere in the code. Before or after any statement, more flexible than wrapping at the call boundary. You don't have to use conditional compilation and pollute your production code stream, and you don't have to use a debugger, which is non-repeatable. Types of use cases. Inject an error anywhere. Change a local variable. Fire an interrupt. Break out of an infinite loop, which is always a problem for testing. And you could even use it to trial code changes. If you're the tester and you're not the coder, you can say, ha, found a bug, this is the fix, see the fix, it works with the fix, there's the fix file. Go add that to your code. They're controlled by instrumentation. So you do it or you don't do it on any particular build of the test. Injection is stored as a snippet file, very easy to read, and it's used with each custom code injection in the test properties for each script. So, when it comes to test execution, one of the things that sometimes happens is that people test unit tests on host because it's cheaper and easier and faster and you don't have the physical hardware in the loop, and sometimes you do need to test on the hardware, so you do both. And platform differences can be verified by running tests on both. The way that Cantata is structured, unlike an xUnit framework tool, because basically you build the test for the environment, so you have a whole duplicate of your tests for your host and a duplicate of your test for your target. Cantata has platform-independent tests, pulls in the software under test, takes a copy of the source code, so your production code is never modified by any of this clever white box instrumentation or code coverage. It has a platform specific, so for example, for a host test framework, pull the options, you build your test, you run it, bang, you get your results. How you run it could be anything. You could run it on a command line, you can run it under all millions of IDEs, you can run it Eclipse, VS Code, everything the way that people might like to do. But if you're going to do it cross-compilation, you get to choose. You have different configurations of Cantata set up for using different cross-compilers and different target environments. So you can have a target test framework that builds a different executable, the cross-compilation one, which is then flashed to the board. Connections of various types. When it's run on the target, you get output. Now, not everybody has super file I/O on a big fat RTOS. Most people don't. I'd say about 90% of our customer base don't, so we use an automatic multiplexer and demultiplexer to take character streams or flush memory buffers or whatever from target to host. Sticking it into a CI/CD, Cantata makefile system works with existing makefile systems, can be used with an existing code tree if you don't want to use sandboxing. It's basically a hierarchy of gmake files with separate target builds. It also runs with CMake and various other combinations. And it allows you full build for regression testing. Because if you are going to do unit testing, don't just do it once. Keep doing it. That's the whole point. You'll lose all the value if you don't. One of the most powerful things in Cantata hierarchy of makefiles is custom.mk. It's a customizable pre and post build command, so it allows you to do anything. You can trigger your static analysis run with Codesonar at exactly the same time you run a build with Cantata. Yeah, you can plug something into an SCM tool. You can fire the result after the test. If it's a failure, fire up Jira and log a bug track. Yeah, you can stick it in your dashboarding. Touched on pipelines briefly this morning, so just an indication, you run your static analysis before you do your dynamic unit test on host or targets. Again, we Dockerize, it's very simple to do. It's really sensible. Some people use virtual machines, VMs from VMware or whatever, but most people don't. Being able to run it on various host and targets for unit and integration testing, and then you end up with no more manual installations. Deploying the tooling as code, infrastructure as code, if you like that terminology. Automated DevSecOps testing. And one of the things that some of my weird techie colleagues like to refer to, null release minimization. When I change one small thing, what is the minimum set of stuff I have to do? So with our impact analysis, change-based testing, it reduces the minimization. And it's quick. If you do it with a narrow set of focused changes, whether it's requirements changes, code changes, or even test framework changes, minimizing that and doing it at speed means the checking works faster and people are happy to do it continuously. If you're sitting there waiting for an hour for your test to run and you're going to do it that day, you're going to leave it till overnight, how continuous does it become? Efficient reporting. So there is an add-on to Cantata. There's an extra tool if you want it. That gives management data. Yep, we put that all on a server. It's all available on a database with a REST API. There is a web interface for it, but it basically aggregates and basically allows you to slice and dice the data, see it over history of trends and things. You can even differentiate between test runs with different environment variables, so run on this target or this build variant, this compiler version, optimization, whatever. It even allows teams to collaborate because you don't actually have to replicate the environment. You can see the results with all the details. That's an example Jenkins set, mostly for afterwards. You can see all of the different possibilities in terms of pulling it, pushing it, running a test with or without coverage or with or without requirements traceability. The reports are linked from Jenkins or Git, so you can get them directly into Cantata team reporting, and this is the type of dashboarding that you can get. Trending, history, results filtering, etc. Last big difference I touched on with xUnit tools. They are open source. They're not certified or qualified for safety critical use. All of the safety standards say you should use tools that are suitable for use. They all have a tool qualification requirement. How well qualified is this tool for the purpose you're using it? There are different qualifications depending on whether it's a runtime component, for example, an RTOS or a library that you're putting into your production code, or whether it's a verification tool, like a static analysis tool or a unit testing tool. Cantata is independently certified by SGS TÜV. Gosh knows how the TÜV market got suddenly so big and all dominated by the Germans. I don't know why, they've just hoovered up everybody, but we chose SGS TÜV. They certify to the highest level of integrity for all the main standards. We provide a tool certification kit, but it is not just a certification kit with a certificate, it's a certification report, a very comprehensive safety manual, currently 82 pages, I know because I just updated it, standard specific briefings. Again, many tens of pages doing line by line mapping of all the requirements of a safety standard to how you can meet that inside Cantata. We don't just say you can use this, we show you how. For D0178C, the avionics guys, they can't do it with a certificate, so we have to provide them with a tool qualification kit. Our certifiers use the D0178 tool qualification kit materials and all the evidence when they certify our tool. Then you've got the extra problem. xUnit tools don't have certification and qualification. What did we do there? Well, before we said, throw it away. Stick it inside a certified tool. But now we have a different option. Fingers crossed, this works.
Do you need to certify your Google tests? If you are developing safety-critical software to one of these standards, your tools need to be qualified or independently certified as suitable for use. Each standard defines the process required for tool qualification or certification. Google Test, including Google Mock, is not certified as a unit test tool. So what do you do? Well, you could qualify Google Test for your project, or you could migrate all your Google Test cases to a safety-certified unit test tool. Both options are risky, very time-consuming and expensive. Now there's a better option, Cantata Hybrid, a unique solution that runs your unchanged Google Test through Cantata technology to generate standards-compliant test evidence and code coverage from a certified unit test tool. With Google Test alone, your suite uses the uncertified Google Test library in an executable to drive the code and check its behavior. With Cantata Hybrid, a compiler wrapper sets options, reads the Google Test suite, and instruments a copy of the code with Cantata directives equivalent to Google Test macros. The built hybrid executable drives the code and checks its behavior with both Google Test macros and Cantata directives. This parallel execution is possible because the Google Test framework matches the Cantata core technology test harness. When the Cantata Hybrid Test executable completes, both the Google Test results and Cantata results including code coverage are reported. The detailed test and aggregate code coverage reports generated in ASCII and HTML formats are suitable as certification evidence of unit testing for all functional safety standards. Avoid qualifying Google Test yourself, creating requirements and tests for every macro used. Avoid migrating tests, buying a certified tool, and risking incorrect transfer of data. Avoid learning a completely different unit test tool. Cantata Hybrid runs all Google Test Suites on Change, on any host or target platform, and includes code coverage up to MCDC. If your Google tests don't deliver 100% code coverage or meet other test objectives, standard Cantata can be used to plug the gaps. Cantata Hybrid is certified for use across all safety-critical industries. This hybrid of Cantata and Google Test delivers a fully automated certification engine for Google tests.
Thank you. That's my time up. Any questions?